So into chapter 18, we are talking about global climate change. So this is what is commonly known to as commonly referred to as global warming. And we are going to first talk about climate in general, so then we can talk about how and why it's changing. So climate influences basically everything around us. And climate change looks to be the phenomenon that most shapes the near future for young people. So in one way or another, the acceleration of climate change will affect each and every one of us for the remainder of our lives, or so claims your book. So climate describes an area's long-term atmospheric conditions. This includes temperature, precipitation, wind, humidity, barometric pressure. This is air pressure, like high and low pressure systems we were talking about, and solar radiation. So how much sunlight does it get? This is different than weather, which includes specific conditions over hours or days, where climate is over years, decades, or centuries. So global climate change is what this chapter is about. It's usually just called climate change. It describes changing in temperature, precipitation, and the frequency and intensity of storms around the world. And global warming refers specifically to an increase in the Earth's average temperature, but it is only one aspect of climate change. So that is why global warming isn't really a correct name for it, because there's more happening than that. And actually your book says that both warming and change sound kind of mild, like it's getting a little bit warmer, it's changing, and so they think that it actually, a better name would be global climate disruption, because we are completely changing and messing with, in a not positive way, the climate that has been given away for many, 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 many years. The climate is complex and finely tuned, and in the past, rapid and disruptive changes have led to mass extinctions. And so that is what some people are so worried about, because we really rely and learn to live, not just us, but all living things, based on the climate that we're in. So if we change the climate, we could lead to that mass extinction, that sixth mass extinction that we've talked about. And this is currently being led by fossil fuel consumption and deforestation. Those are the two biggest causes. The Earth's climate varies naturally, but disruptive changes are unfolding rapidly, with human activities such as deforestation and fossil fuel combustion accelerating them. So there are three factors that influence climate. The first is the sun, which provides light and warmth. Without the sun, we would be dark and frozen. The atmosphere, which prevents major temperature shifts from day to night. And without the atmosphere, the Earth would be as much as 33 degrees Celsius, so 90-ish degrees Fahrenheit, colder on average, and the temperature between night and day would be much, much greater, because the atmosphere tempers the sunlight in the day, so we don't get too much of the heat or the radiation by reflecting a lot of it back, and it keeps the heat in with the greenhouse effect at nighttime. So if we didn't have the atmosphere, it would be much hotter during the day and much colder during the night. And then the oceans, which store and transport heat and moisture. So the sun supplies most of our planet's energy, which the atmosphere absorbs or reflects most of it before it even reaches the surface. So this yellow stuff right here is the solar radiation. So this is what the Earth receives. So if we're saying that most of that is 340, that's the highest level that we're coming in. So a lot of it is absorbed by the atmosphere. A lot of it is reflected by the clouds, aerosols in the atmosphere, bounced back into space. And a lot of it is absorbed by the Earth's surface and the ocean. The shorter wavelength UV and visible light pass through the atmosphere. Then some of it is reflected by the surface. So in total, there's about 100 watts per square meter reflected by the surface out of the 340. Then what happens is so the atmosphere, clouds, land, ice, and water absorb 70% of incoming solar radiation, and 30% is reflected back. The 70% that is absorbed powers everything from wind to waves to evaporation to photosynthesis. So remember that energy can come in many forms. One of them is sunlight. And so the sunlight that we get from the sun or the energy that we get from the sunlight can then be transferred into other forms of energy that power things, like we said, like photosynthesis, like the waves, like wind, like evaporation. So that's where the grand majority of Earth's energy comes and has always come from sunlight. So a lot of when it gets bounced back, it's infrared radiation. And so it's just all electromagnetic radiation. That's things like light, microwaves, radio waves, UV light, infrared light. It's just waves that are at different wavelengths. So when it bounces back, it has a longer wavelength, and so now it is infrared radiation, and it's re-emitted after it has been absorbed, and so re-emitted. So a lot of the radiation is sent back from, it was absorbed by the atmosphere, and then it's re-released by the atmosphere. A lot of it is re-emitted by the surface, so a lot of it, but only some of it passes through the atmosphere that is re-emitted from the surface. A lot of it then stays here. We also lose some through evapotranspiration, so when the plants do photosynthesis and lose energy. And the greenhouse gases in the atmosphere cause much of it to bounce back to then be absorbed by the surface again. So greenhouse gases are atmospheric gases, so gases found in the atmosphere that have 3 or more atoms in their molecule, 3 or more atoms together. They tend to absorb this infrared radiation given off by the Earth's surface. They tend to absorb these orange arrows and send it back downwards. These are called greenhouse gases, and they include water vapor, ozone, carbon dioxide, nitrous oxide, methane, and halocarbon. So there's many different kinds of greenhouse gases. So these gases re-emit in all directions, but much of it comes back down to the Earth's surface and warms the lower atmosphere. And the rewarming of the lower atmosphere by this is called the greenhouse effect. So greenhouse gases give us the greenhouse effect. And not all gases will warm the same. So I said we have different gases. So global warming potential is the relative ability of a greenhouse gas molecule to contribute to warming. So some gases will warm better than others. The values of global warming potential are expressed in relation to carbon dioxide. So carbon dioxide's ability to warm is 1, and so everything is expressed in relationship to that. So for example, methane is, its level is 84, its heat trapping ability, and so that means it's 84 times, you would need 84 carbon dioxides to get the same amount as 1 methane. So it is much stronger. However, methane's residence time in the atmosphere is a lot less than that of a carbon dioxide. So carbon dioxide is far more abundant than most other greenhouse gases because its residence time is so much longer and we're releasing so much of it. So even though methane and nitrous oxide and halocarbons have more heat trapping ability, there's so much more carbon dioxide that it has a much greater effect. So most of our emissions from humans are carbon dioxide, and it has caused nearly twice as much warming as methane, nitrous oxide, and halocarbons combined since the Industrial Revolution, because we have released so much of it. And this shows the difference in 20 years over 100 years. So methane's ability to warm lowers, the others don't, but methane isn't as good at warming over years, but carbon dioxide will stick around and keep warming. So these greenhouse gas concentrations are rising really fast. The greenhouse effect has been present in the entirety of the Earth's history as long as there's been an atmosphere, and it has kept our planet warm enough to support life. So if we didn't have the greenhouse gas effect, it would not be warm enough here for living things to be. However, so greenhouse gas is actually beneficial, but the anthropogenic intensification, so it's gotten more intense because of human activities. It worries scientists because over the past 250 years, humans have caused a net accumulation of greenhouse gases in the atmosphere, primarily due to the release of carbon in fossil fuels during combustion. So we have boosted the CO2 concentration from 278 to 400 parts per million, so of a million gas molecules. It used to be 278 were carbon dioxide, now 400 are, from the 1700s to today, and it's probably the highest it's ever been in the past 20 million years. So a very, very long time. And the reason why it's risen so rapidly is that most carbon is stored for long periods of time in the upper lithosphere, so in the ground. And this turns into fossil fuels over time. And then we take these fossil fuels, so we take them from their sink in the ground and we burn them and release it to the atmosphere. So normally it's stored for millions of years underground, and instead we take them and release them to the atmosphere. So the combustion of fossil fuels transfers carbon from one reservoir, the underground deposits, to another, the atmosphere. And then we also chop down forests. And what that happens is, remember, it doesn't just poof release carbon dioxide into the atmosphere, but now we took away the method of removing the carbon dioxide from the atmosphere. Remember that through photosynthesis, we remove that carbon dioxide from the atmosphere. So when we cut down the trees, now we are increasing the amount of carbon dioxide in the atmosphere, and we took away the way to get it out. So all we're doing is increasing the amount of carbon dioxide. You can take a look at this. The green are the natural ways that carbon dioxide enters and leaves the atmosphere and the ocean, and then the red ones are the anthropogenic, the ones that humans have done. Oh, then we also have nitric oxide in the atmosphere increasing, primarily due to auto emissions, feedlots, and the use of synthetic fertilizers. It's risen 20% since 1950. And then we also have the ozone concentration in the troposphere has grown, which is a result of photochemical smog. This has risen 42% since 1750, but it's slowed down because of the Montreal Protocol. And actually, the most abundant greenhouse gas is water vapor. Its concentrations vary locally. Obviously, if you're closer to the ocean or a body of water, it'll probably be higher. But but because its global concentration hasn't changed, it is not thought to have driven industrial age climate change. So then we have these things that are called aerosols. And aerosols are microscopic droplets that can have either a warming or cooling effect when present in the atmosphere. So they're teeny tiny little droplets. We have what's called soot particles, or black carbon aerosols, which cause warming by absorbing solar energy. So basically they get into the air and they absorb solar energy and make the atmosphere warmer. But then there are other aerosols, such as sulfur, that reflect solar energy and have a cooling effect. So a lot of times, or in the Earth's history, there have been volcanic eruptions that release a lot of these aerosols, and then it actually lowers the Earth's temperature by a few degrees for a short amount of time because it reflects so much energy back. So feedback loops make this tough to predict what's going to happen. So as tropospheric temperatures increase, more water should evaporate and enter the atmosphere. So as we're increasing the temperature of the planet, that's going to lead to more evaporation, because as we heat up the water, it's going to evaporate. So there's two different ways this could play out. One is that it will be a positive feedback loop. So more atmospheric water vapor will be a greenhouse gas and will lead to more greenhouse effect, warming the temperature, thus causing more evaporation. So now we're in a positive feedback loop. More evaporation means warmer temperatures, means more evaporation means warmer temperatures. But it could also, what it could do is then it could enhance cloudiness, because as we increase the water vapor, now as that air rises and cools, it's going to lead to increased clouds and precipitation, which could reflect the sunlight back to space and slow the warming down in a negative feedback loop. So we are not sure which one would happen or how the balance would vary from place to place. And the reason that climate varies naturally, so we do have changes naturally in climate over years, and there's a few of them. One is called the Milankovitch cycles, and that is that over thousands of years, the Earth wobbles on its axis a little bit. We'll go from 22 degrees to a little bit greater, 25 degrees and back. And it experiences changes in the shape of its orbit. So the Earth orbits around the sun, and sometimes it's a little bit longer, sometimes it's a little bit shorter. And these changes vary naturally, and it changes the Earth's climate, because if we're getting closer to or farther away from the sun, that would change the amount of solar radiation we're getting. Also, another reason why our climate varies naturally is that the sun varies in the amount of radiation it emits. So some years we get more sunlight than others, just because the sun varies on how much sunlight it's giving off. And scientists believe this has not had a significant effect on the Earth's average surface temperature. Then we also have the oceans. The oceans hold 50 times more carbon than the atmosphere, but we are absorbing less carbon dioxide than we are adding to the atmosphere. So basically, the oceans can store carbon dioxide for us, but as they warm, they cannot hold as much carbon dioxide. So it's a positive feedback loop that accelerates the warming. So as the carbon dioxide causes the planet to warm because it's a greenhouse gas, which causes the ocean to warm, and then that warm ocean can hold less carbon dioxide, so it releases more carbon dioxide, which then leads to more warming, which increases the temperature of the ocean, which means it can hold less carbon dioxide. So it is a positive feedback loop. Then we also have the thermohaline circulation of the oceans, which moves warm tropical water north, where the heat is released from Western Europe. So this is what we were talking about, where as we warm, then the glaciers by Greenland might melt. That would change the currents and change the warm water that is being brought to Europe, which is warming it, and it could drop Europe into much colder conditions. Then we also have climate variability from things like ENSO, the El Nino Southern Oscillation.